Hi everyone, my name is Andrew Wagenmaker. I'm a PhD student at the University of Washington, and today I'm going to be discussing our paper, Active Learning for Identification of Linear Dynamical Systems. This is a joint work with my advisor, Kevin Jamieson. So in this work, we're going to be looking at linear dynamical systems with observable state of this form, xt plus 1 is equal to a star xt plus b star ut plus a to t. Here xt is some observed state, ut is an input that we will get to choose, a to t is unobserved process noise, which we assume to be Gaussian, and a star is our unknown system matrix. This is the parameter we want to learn, and we assume this is stable, meaning the spectral radius is less than 1. And then b star is the control matrix. In this paper, we're going to assume this is known. So why look at linear dynamical systems in the first place? Well, linear dynamical systems are a ubiquitous paradigm. It's used to model a wide range of real-world phenomenon. So much of control theory is based on linear dynamical systems, but it also has applications in other fields such as econometrics, time series modeling, and a variety of other domains. So as a practical example of this, we could think of a drone. The actual dynamics governing its motion are likely nonlinear, but we can come up with a linearization of the dynamics around some equilibrium point. And we can use these then to do controller design or a variety of other downstream tasks. So in many cases, you can simply come up with a model of your system from first principles using physics. But in some cases, that's not possible. And so in these cases, where we want to build a model of our system, we use system identification. Basically, we have some input-output data of our system. How do we fit a model to that data, which describes the actual motion of the system we've observed? And this itself is a basic step in controller design and model-based reinforcement learning, and potentially a lot of other domains. And so in this paper, we're going to be trying to answer this question. If you're given complete control over the inputs to a dynamical system, how can they best be chosen to most effectively estimate the system's parameters? So we're going to be doing system identification, but we want to do it in an active way. And so more formally, we can pose it as this problem. Given our linear dynamics, which we already stated, how do we choose ut to estimate a star as quickly as possible while satisfying some power constraint on the input? We have this power constraint just to ensure we can't make the signal-to-noise ratio arbitrarily large. And in this paper, we're going to be interested in quantifying the error in the matrix 2 norm, the operator norm. So this is not a new problem. There's a large body of work out there that investigates this problem, how to do input design for excitation. This goes back to the 70s up to the present day. Now, the shortcoming of all these works is that they tend to lack theoretical guarantees or explicit algorithms. They tend to be much more ad hoc and propose heuristic methods that they might validate with several experiments but don't really formally justify. More recently, there's been some interest in the machine learning community in system identification and applying machine learning techniques to control problems, and in particular, developing finite time bounds on estimating dynamical systems. And so two relevant papers, Simkowitz et al. And Sarkar and Rocklin from 2018, basically solve problems similar to ours, but the bounds they provide only work when the excitation is due to noise. And as we're going to see, this is actually insufficient for optimal excitation. So in this work, we're actually the first to rigorously study this problem of active input design. We present the first provably correct algorithm that solves it. So we'll propose an algorithm, and then we're going to show that it's asymptotically optimal. And we also give finite time performance guarantees. And from a technical standpoint, the primary novel tool we come up with is a finite time bound on estimating dynamical systems when non-noise inputs are being played. Before we get into the results, I want to just go over some preliminary points. So let's say we're given some sequence of states and inputs that were generated from a trajectory of our dynamical system. Then we're going to estimate a star by simply solving a least squares problem. So again, remember, b star is known. And so we're just going to find the a that sort of minimizes the least squares cost from our observed data. And this is a least squares problem. We can just write down the solution in closed form. And if you do that, you see that it's the following. That a hat is equal to a star plus this error term. And this error term is basically the inverse covariates, xt transpose inverse, times this other term, which sort of corresponds to the interaction between the states and the noise. So if we want to bound the error, we can just sort of do so as follows. Again, if we're looking at a hat minus a star in the spectral norm, we can write it down like this, and then we can upper bound this by pulling out sort of 1/2 of these covariates. And if we do that, then we get this top term here, which is the covariance to the negative 1/2 times this other noise term. And then that's divided by the square root of the minimum eigenvalue of the covariance. And this top term is a self-normalized term. And we're not gonna spend too much time on it in this paper, but the bottom term is really the key point. And you can see that the error critically depends on the minimum eigenvalue of the covariance. So to make the error small, we want to sort of excite the system and increase the minimum eigenvalue. And that's sort of the approach we're going to be taking in this paper. So some notation really quick. We're going to define gamma k to be the expected covariance due to noise. So if we don't feed any input into the system and it's just excited by this noise, gamma k is going to be equal to s equals 0 to k minus 1, a star s transpose. And gamma ku is the expected covariance due to the inputs. In this case, we're going to say that our input has period k, our noise we set to 0, and gamma ku then corresponds to the steady state covariance obtained by playing this input on our system. And so gamma ku fundamentally depends on a star through xs. Xs is sort of the state produced by our dynamical system, which has a star as a parameter. And so gamma k and gamma ku sort of quantify the basically the excitation due to the noise and the excitation due to the inputs. And as we'll see, these quantities pop up in our bounds. So first I'm going to present this lower bound. Let tau epsilon delta be the minimum number of samples needed for a hat minus a star is less than epsilon with probability 1 minus delta. Basically, we get a good epsilon good estimate of our system with high probability. So we have the following theorem then. For epsilon delta small enough, any reasonable algorithm requires that tau epsilon delta be greater than or equal to sigma squared epsilon to the negative 2 log 1 over delta divided by the minimum eigenvalue, again, of these expected covariates that we defined on the last page when the optimal inputs are being played. Here, the optimal inputs are the ones that make this as large as possible. And the key term really here is this minimum eigenvalue. This is sort of the piece we're going to be going after. And we can see that to make the sample complexity as small as possible, we want to choose the inputs that maximize this term. And so this sort of then motivates an approach. Basically, we can sort of design our inputs in a way that maximize this minimum eigenvalue, that will best excite the system and it will reduce our sample complexity. Now, unfortunately, this requires knowledge of a star. As we said, gamma u depends on a star. And so you can't actually solve this optimization without knowing a star. But a star is the parameter we want to estimate in the first place. So we have this sort of chicken and egg problem. And this motivates the possibility of perhaps doing something active, and our algorithm is basically going to be going after this directly. But you might ask, even before we start talking about algorithms, could you just achieve this lower bound by playing noise? Do you actually need to do anything more sophisticated than just exciting the system via some sort of Gaussian noise? And so the answer is actually yes, you do. And here's a simple example. Let A star equal V lambda V transpose, where V is some orthogonal matrix. Lambda is a diagonal matrix with elements 1 minus 1 over D. And then we'll just assume B star is identity. In this case, if you set the input to be normally distributed with the optimally exciting covariance, then you can find that the tau epsilon delta is of order sigma squared epsilon to the negative 2 over gamma squared. It's important to note here, this is not simply isotropic noise. This is if we actually knew the system and we could solve for the optimal covariance. This is not something that's implementable then. But even in this case, this is a sample complexity you get. But you can show from a lower bound that the actual lower bound on the sample complexity in this case is sigma squared epsilon to the negative 2 d gamma squared. And so in this case, plain noise, even the optimal noise is suboptimal by a factor of d. And in fact, you can make this arbitrarily suboptimal by letting the eigenvalues go to 1. And so we see then from here that excitation via noise is not the optimal thing we can do for system identification. We actually need to do something more, and that's sort of what we're going to be proposing here. So here's our algorithm. I'm just going to quickly walk through it. Basically, you start with some input power, gamma squared, and some initial epoch length t naught. And then we're going to run our dynamical system for t naught steps, just playing isotropic noise. Given that data, we're going to find an initial estimate, A naught hat, of our system matrix. And with that estimate, then we're going to optimize for the best inputs that would optimally excite our estimated system. So if A naught hat was our true system matrix, U tilde 1 is going to be the inputs that would optimally excite that system. And then we're going to iterate on this. We're going to increase our epoch length We're going to run our LDS again. And now we're going to be playing inputs that are a combination of noise and the inputs we just solved for to be optimal. We're going to come up with a new estimate of our system from this data, and we're gonna find a new set of inputs. We sort of just are going to keep repeating this. We keep increasing the epoch length, finding an estimate of the system, and updating the inputs. And running this algorithm, we have the following theorem: for small enough epsilon and some universal constant c, the estimates produced by our algorithm satisfy the limit as delta goes to 0, tau epsilon delta over log 1 over delta is upper bounded by some constant times sigma squared epsilon to the negative 2, divided again by this minimal eigenvalue when the optimal inputs are being played. So we see that up to constants, our algorithm is asymptotically optimal. And of course, then in the example where the noise is suboptimal, our algorithm achieves the lower bound. And so we have here then an algorithm that provably it improves on simply exciting a system by noise, and that provably gets the optimal sample complexity. So to prove this result, the sort of primary technical tool that we came up with is bound on the estimation error in finite time when you're playing some arbitrary non-noise input. So as I mentioned, existing estimation bounds only apply if the input is normally distributed. And as we just saw, this doesn't yield optimal rates. So we proved the following theorem: assume ut is some deterministic signal. It's periodic with period k and its average power gamma squared. Let TSS be something on order 1 over 1 minus the spectral radius of A plus k times d. Then as long as t is greater than TSS, with high probability, we will have that the estimation error is on order sigma squared times d, square root of sigma squared times d, divided by t times the minimum eigenvalue of the expected covariance. The key term here is that we have this gamma ku in our bound. So again, existing bounds do not have this gamma ku in them. Ours is the first to get that in there. And this is really sort of the key term that allows us to get the optimal estimation rates. In proving this theorem, the primary technical challenge was handling correlations between states, since our system, our states are generated from this random process that has these correlations, and in handling the interactions between inputs and noise. I'm not going to go into the proof here. You can look at the paper for that, but that's sort of a gist of what we tend to deal with. And so given this result, we were then able to prove basically this asymptotic result, but we were also able to prove a finite time result on the performance of the algorithm itself. And I'm not going to state that in full generality. You can look at the paper for that, but the sort of, here's one corollary in a simple case just to give you some flavor. So assume A star is symmetric and has eigenvalues lambda 1 to lambda d. Then our algorithm will produce estimates satisfying with high probability square root of sigma squared 1 minus lambda 2 norm squared divided by gamma squared times square root of t over d. And this holds so long as t is greater than 1 minus lambda to the fourth. You can think of this as the average gap to the fourth, divided by gamma squared 1 minus lambda 1 to the fourth. So that's sort of like the worst case gap, the smallest gap to the fourth. So you can see there's a trade-off. As lambda gets closer to 1, our estimation rate gets better and better. But as lambda 1 gets closer and closer to 1, our burn-in time increases. And basically, this burn-in time comes from basically the amount of time needed for our algorithm to guarantee it has a good enough estimate of the system to be playing close to optimal inputs. We can contrast this with just plain isotropic noise. And in that case, we're going to get estimates that satisfy the following: basically square root of sigma squared d over gamma squared times square root of d over t. Here, the important constant is this 1 minus lambda squared versus this d. And so in our case, we can adapt to the underlying structure of the A matrix. Whereas if you just play isotropic noise, you can't take advantage of that at all. You're always just getting hit by this factor of the dimensionality. And here are some experimental results just to sort of show that this works in practice. So in this case, we're going to have several things to compare against. One is just isotropic noise in orange. In green, we're going to have the response when you, or the error when you play the optimally exciting noise. Red is our algorithm and blue is the oracle, if you just solve for the optimal inputs from the start. And you can see in both the examples for randomly generated A star and for symmetric A star, our algorithm significantly outperforms just plain noise and gets pretty close to the oracle performance in both cases. That's what we have to talk about. Thank you for watching.